everyone. Here is the outline of my presentation. At the first, I'll begin with a brief introduction to problem and motivation. And then I'll describe the proposed converter topology and its key components. After that, I'll explain the integrated voltage clamping circuit that helps protect the system and improve efficiency. We'll then look into the soft switching condition, especially how ZVS is achieved. Next, I'll show simulation result and analysis to demonstrate the converter performance. I'll also provide a comparison with other similar topology, and finally I'll wrap up with the conclusion, highlighting the benefits and application of this design. As electric vehicles, renewable energy, and smart grid grow rapidly, our energy systems are become more contributed and intelligent to manage power efficiently between batteries, supercapacitors, and DC link. Bidirectional DC-DC converters are essential. These converters must be compact, fast, efficient, and produce low EMI to meet the demands of modern energy applications. This presentation introduced the new bidirectional DC-DC converter designed and meets this need using magnetic coupling and soft switching techniques. This slide shows the structure of the proposed converter. It used a QZS network combined with coupled inductors to enable efficient bidirectional energy transfer. The converter step up voltage from a low voltage source like a supercapacitor to a higher voltage level. It includes 3 switches, 2 main capacitor and a filter capacitor on both voltage sides. Magnetic coupling helps reduce switching stress and improve efficiency, while the QZS network ensures good control and voltage boosting ability. In this slide, you can see a figure. This figure illustrates the main waveforms of converter during the operating modes. The gate signal for Q1, Q2, and Q3 will be VG1, VG2, and VG3, and the voltage stress and current through switches will be VG1, VQ1, VQ2, and VQ3, and IQ1, IQ2, and IQ3. In this slide, I want to explain different states for this converter. In the first state, Q1 and Q2 are turned off. Their parasitic capacitors CS2 and CS3 begin to charge due to the current from the inductors, while the parasitic capacitor CS1 discharge. The result voltage across the capacitors can be described using the following equation. In the state 2, the main switch Q1 is turned on under ZVS condition. L1 energized by DC source and LVS and causing the inductor current to increase linearly. Lm and C2 are connected in series and are charged by C1. In state 3, Q1 is off and CS1 is charged by CS2 and CS3. Since the voltage of the large capacitor are assumed constant after the synchronous charging and discharging of CS1 with CS2 and CS3, Q1 is fully turned off, while the freewheeling diodes of T in Q2 and Q3 begin connecting. In the state for Q2 and Q3 are on. During this period, the LVS source charge L1 and C1 while also connecting in series with C2 to supply energy to HVS level. The conducting current of Q2 and Q3 reduce along with the decrease in inductor current. Different equation for in this states illustrate in this place. In the real world converter design, leakage inductor can create voltage spikes that stress the main switch. To handle this, our converter includes an active clamping circuit made of two additional MOSFET and capacitors C1 and C2. This setup acts like a regenerative snubber. It captures and recycles the leakage energy instead of wasting it as a heat. This not only protect the switch but also improve the system's overall of efficiency and reliability. In this slide, I want to talk about the concept of ZVS. Ensures switches turn on at ZVS minimize switching loss. This condition requires parasitic capacitor of switches to fully discharge before switching on. Now I want to know how ZVS is achieved in this converter. We consider a dead time a really brief period when all switches are off. During the dead time, freewheeling diode connected. Reverse inductor current discharge parasitic capacitors, and Q2 and Q3 function as a synchronous rectifiers. Energy from inductor current during the dead time must exceed energy stored in parasitic capacitors. As a result, our switches achieve ZVS on in both directions. Reduce switching lasts and EMI, improve overall efficiency and reliability. In this slide, you can see different parameters that are used for simulation. The simulation conducted in VLO 50 volts and power of 310 watts. In this slide, I summarize the simulation result of converter. Under the VSF control, the converter maintains soft switch operating, achieving ZVS for all switches and QZ for Q2 and Q3. The inductor operating in CCM and efficiency peaked at 95% under fixed frequency operation. This article compare the proposed converter with other design based on the components and efficiency. However, in the first converter, however, it introduced a significant high frequency potential difference between the input and output ground. This converter can generate substantial electromagnetic interference (EMI), a factor that makes system stability. Additionally, the design includes four diodes, which inherently reduce its overall efficiency due to increased conduction losses. The second converter has features a common ground design and is capable of achieving a wide range of high voltage gain. However, the inclusion of numerous diodes result in significant conduction losses, which in turn causes the conversion efficiency to decline. Converter use the fewest component among the compared topology. However, they suffer from a discontinuous input current with a high ripple level. In this slide, I want to summarize this work. This article introduced a high performance bidirectional converter using a novel variable switching frequency control strategy. This ensures CVS and QZCS for soft switching, minimize losses. The coupled inductor boosts voltage gain while maintaining a small input current, making the design highly efficient and reliable. This feature makes the converter an excellent fit for modern EVs application. Thank you so much.